Dhaka, Bangladesh, is the world's second-largest city agglomeration, with a population of 36.6 million residents, and its infrastructure is no longer capable of supporting them. The city faces a triad of threats: catastrophic monsoon flooding, hazardous air quality that averages 5 times the WHO limit, and the looming risk of a magnitude 7+ earthquake. Traditional city planning operates in isolated silos. When monsoon bursts hit, the 80% impermeable surface forces runoff into drainage systems already clogged by uncollected waste, trapping water for weeks and weakening the foundations of buildings that were never designed for seismic stress. This physical fabric has become a liability. Unregulated growth ignores seismic codes, while the spread of concrete traps floodwaters on the surface, preventing natural infiltration. Static infrastructure cannot survive these dynamic compound crises. The city's very foundation has now become its primary point of failure. This is APHQI 10.0. It is a proposed framework that shifts urban design from a collection of static buildings into a living, predictive nervous system. By ensuring every subsystem communicates in real time, the framework converts overlapping hazards into interacting solutions. To see exactly how this works, we will stress test the framework by simulating a catastrophic monsoon and a massive earthquake. Urban survival now depends on moving from resisting nature to anticipating and absorbing it through predictive AI and adaptive engineering. The first simulation initiates a devastating 100 mm/hour monsoon burst over the city grid, pushing the drainage system to its absolute limits. The defense is led by long short-term memory AI models. By processing 15 years of local climate data, the system maps flood risks 3 full days before the rain falls. As the rain hits, the street-level system responds. The water is absorbed by permeable concrete roads capable of drinking 2.8 millimeters per second. These surfaces are constructed from recycled plastic waste, providing a physical use for urban pollution, while providing 90% runoff reduction. By combining predictive mapping with high-speed infiltration, the city effectively drinks the flood rather than drowning in it. Next, we trigger a magnitude 7+ earthquake simulation, shifting the stress from the sky to the subterranean utility network. Below the surface, utility corridors employ 3D base isolation. While the outer shell shakes, inner lines for power and water remain stationary, preventing cascading blackouts. At the surface, neural networks monitor structural health. Sensors detect anomalies, triggering automated evacuation alerts in under 50 milliseconds. Buildings rely on replaceable structural fuses. These components absorb 80% of the seismic energy elastically, preserving the integrity of the main gravity frame. These fuses can be replaced within 24 hours. Conventional concrete retrofitting for the same level of damage would take up to a year. In seismic engineering, designing a building to yield predictably and heal rapidly mitigates 71% of structural damage compared to rigid concrete designs. During peacetime, quantum optimization algorithms act as a master conductor, managing the daily energy grid and ensuring peak efficiency across the city. The circular economy system captures 6,000 tons of daily urban waste, achieving a 90% diversion rate. Organic waste is converted into biogas for renewable energy, while inorganic plastics are pyrolyzed into the eco-blocks used to pave the streets. This integration extends to agriculture. Bifacial solar panels generate clean baseload power while providing the necessary shade for high-yield mushroom farming beneath them. Environmental sustainability is engineered as a closed loop, where the waste of one system becomes the foundational fuel for the next. This data compares the failing infrastructure baseline of 2025 against the results of an optimized APHQI city. Flood durations drop by 94%, seismic damage is mitigated by 71%, and carbon emissions are reduced by 60%. Financing this transition requires an initial $5.2 billion investment, but the framework generates a $15.4 billion net present value over 20 years. This return is driven by extreme operational savings and circular economy value, and the avoidance of billions in projected disaster damages. By merging predictive AI with adaptive engineering, cities in the Global South can convert their highest-risk climate and seismic hazards into a $15 billion net economic surplus.